Okay, in this video we're going to finish up pages 10 and 11 of Notes 2. And we're going to do it all on the calculator because it's a little faster. Or at the very least it's less writing. So what I'm doing is defining a function. Hopefully you know how to do that. I like to look at I need to make the table if I'm going to write a Taylor polynomial that has 4 non-zero terms. What I'm going to do in this case is use the listen spreadsheets to do that. So I like to name the columns, but you definitely don't need to do that. The third column is supposed to be the derivative at the center, so I usually just name it at, and then whatever number the center is, so at 1 in this case. I don't think any of these derivatives are going to be 0 when I plug in 1. So I'm just going to go to the fourth derivative, which gives me the 0 through fourth, so it should give me 4 non-zero terms plus the extra derivative that I'll use to figure out a value for m or bound on that. So here what I do, press equal, and then I go here, and I want the derivative with respect to x. And then the order of the derivative, I'm going to use a1, so whatever's in a1 becomes that value. So fx. And now what I'm going to do is just grab this corner here, so you click and grab, and just kind of drag it down. And one more. There we go. And then I do something really similar here, so I'm going to type equals, and then I want b1, so whatever's in b1, and then control equals, and go here, such that, and then x equals 1, because I'm evaluating everything at 1. And then I will drag down again. Here, 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 and there. Okay, so the first 4 things here give me non-zero terms. So if I go with a Taylor polynomial, a third degree Taylor polynomial, then the fourth derivative I'll use to figure out the value of m. So it should be good. Okay, so here, I'm going to use built-in Taylor polynomial, menu, and then calculus, and series, and then Taylor. So it's the function, the variable in the function, the degree that you want, and then the center. So it gives me that, and I want to store that. So p of x set equal to the answer. So answer, by the way, for you is control and then the negative sign. It's just faster for me to type. So now I can do p of 1.3. So that's my approximation. To get the error, I said I went to the third degree there, so I need the fourth derivative. You can see the denominator will increase as x increases, so the function is decreasing, which means that it has its maximum at the left end point of the interval, which is from 1 to 1.3. So if I do such that x equals 1. So that's the value of m. That's the actual value of m. I don't need to kind of bound it in this case. So e, the error, is set equal to m times, it's the absolute value of 1.3 minus 1, but that's just 0.3, so I don't really care. And then if this was up to the fourth derivative, this will be the fourth power, or fourth factorial. Enter. So that's my error. So my range, 1.3 minus e, p of 1.3 plus e. It's a pretty small error. Is that, and then the actual value, if I just want to figure it out, is that. So it's definitely in my range. So success. And I will move on to the next problem, which I don't know if it'll go any faster. I would like it to go a little faster because I feel like we kind of know what we're doing now. So cosine of x squared. I'm going to use my table again. It's actually easier for you if you just reuse that previous table. Like maybe don't start a new thing, but whatever. Derivs, and then this one is centered at 0. It's really useful to name that column. So equals sequence, seq, t, comma, 0. With trig functions, you just kind of never know what's going to be 0. So I need 3 non-zero terms, so I'm just going to go to 8 and see. I mean, I got to get that many in that interval. And here, remember, it's the derivatives, and then a1. So there's just no chance that you're keeping up with me at this point. But that's okay. Then I drag down, because you can pause this and rewind, or whatever. And then here, I want b1, such that x equals 0. So it's b1 such that x equals 0. Plugs it in for me. And now you'll see, I think every other one is going to be 0. Yeah, so there, that took me to 3 non-zero terms. So that's all I actually need, right? It's 1 and then 0 and then another number and then 0 and then another number. So that's 3 non-zero. So if I go to the fourth degree Taylor polynomial, I'll get 3 non-zero terms. So let's do that. So it's Taylor f of x, comma x, comma 4. So that's what I needed. I'm going to store that as p of x. And then if I do p of 0.5, it gives me my estimate. Now the real question is, how wrong could that be? So I went to the fourth degree here, so I need to look at the fifth derivative, the n plus first derivative. So f of x, I get that. So this is a trig function. Trig functions are kind of complicated. So one thing you might do is just graph the absolute value and look at it. You might be getting the sense that 32 is the maximum that we could achieve. But what I'm going to do is actually something a little different. I'm going to do menu, trig, and then collect, because I kind of recognize that as the sign of 2 something. Well, sign of 2x. So if I do trig collect on that, and then remember I'm supposed to be looking at the absolute value. So I can see right there the biggest that function could ever possibly be is 16, so I'm going to use 16 for m. So now I can calculate my error. So 16 is definitely greater than or equal to the true value of m. So I feel safe in using it. And then it's the absolute value of 0.5 minus 0, but that's just 0.5, so I'm not too worried about the absolute value part. To the fifth, and then over 5 factorial, which gives me that, which is a very small value for your error. Or at least I think it's small. It's probably not very small if you're like designing a rocket ship, but we're just doing a problem, so it's okay with me. So p of 0.5 minus e, p of 0.5 plus e, or I'm using e for error, which is kind of a little confusing because e is also a number, but I get that. And then if I just do f of 0.5, I get a number that is actually in the interval. So it worked out. Okay, one last problem. It's actually kind of maybe the weirdest one. So I'll insert a new problem, calculator page, I'm going to define my function. So I'm just doing the same thing over and over at this point, which is why I'm not being particularly talkative about it. Name my columns. This one is being centered at 3, which is kind of a little weird. Sequence t, comma, 0 to, I don't know, I'll go out to 5. I mean, I need 4 non-zero terms, so hopefully none of them are 0, and going out to 5 will give me enough. Okay, and then here, it's the derivative with respect to x, a1, f of x. So this is why you want to store things, so you can kind of just go through and use them later on. Yeah, there we go. And then let me go one more just in case, but I think I actually maybe went too many because if I need 4 non-zero terms, I'll probably get those here, and then this is the extra one. So I probably don't need this, but whatever. And then b1 such that x equals 3. And that's probably, that's the main reason I started naming the columns. So you can see I get non-zero terms here, so 4 non-zero derivatives means that the next one, that'll give me 4 non-zero terms in my Taylor polynomial, so the next one will help me find the error. So let's go back and do that. So I want to do Taylor f of x, variable, the degree, so that was, I already forgot. Yeah, I want to go to 3, so 3. And then the center, which is also 3. So there's my polynomial. Store that. So that. And now I can do p of, problem says to do 2.77, so whatever. So I get that. And now I need to figure out the error. So I went to 3 here. That was my degree. So I want the fourth derivative. I need to look at that. x4 f of x. Okay, and then don't forget we really want the absolute value of that. And we're going to search on the interval from 2.77 to 3. So if we think about this, as x increases, so it's 1, and then it's 2, and then it's 3, the denominator actually gets smaller, right? So you're taking a number and dividing it by a smaller denominator, which means overall the thing will be getting bigger. So this is actually increasing. So if I evaluate this at 3, because I'm only allowed to look from 2.77 to 3, that actually gives me the value of m that I want. So that's not an approximation of m, that's m. So my error is the answer, the previous answer, so 15 over 2048 times the absolute value of 2.77 minus 3 to the, what derivative are we looking at here? Fourth. So to the fourth over 4 factorial, which is ridiculously small. So that's a very small error right there. And so if I do p of, what am I approximating? 2.77 minus e, and p of 2.77 plus e, you can see that to 4 decimal places, we kind of nailed it. So if I do f of 2.77, there it is. I think maybe it'd be really interesting for this particular problem, since it's so close, if we look at a graph. Let me insert a graph. I'm going to graph f of x, and then I'm also going to graph p of x. And you can see that they're super close to each other on this interval. Actually, from whatever this is until 0, they're really good. So that's why we're getting such a really close estimate. But anyway, that's those problems. I didn't feel like handwriting them. So also, it gives you a chance to see how the Nspire handles it. And I hope you found this helpful. Good luck.